And please stop me and ask questions if you have questions. So this is important stuff, and it's going to keep coming up. So if you had trouble with any of these, you need to figure out what the problem was, and one way to do it is to watch me go through it and then find the place where what you were doing took a wrong turn. Yep. This will, yes. But you should still pay attention right now because otherwise it's not as much fun for me to say this stuff. And that's important. Okay, number one. So this says, number one says a ball is thrown straight up into the air with a speed of 20 miles per hour and a height of 3 feet. So it starts out with a height of 3 feet. Starts out with a speed going up of 20 miles per hour. I'll write it like that, 20 miles over hours. And it asks first, what's the height of the ball when it reaches the highest point? And it asks for it in miles and in scientific notation. And then second, how long does it take for the ball to hit the ground? Okay, so for part A, this is all straight up and down, so we can do this as a one-dimensional problem. Like all one-dimensional problems, you could do it as a two-dimensional problem, and if you did, in this case, you would just see that you were only dealing with Y stuff, X stuff didn't come up, and it would work out just the same. You just have little subscripts written. So you can, any one-dimensional problem you can do as a two-dimensional problem. Okay, so the first thing we have to do is get all the units consistent. And a lot of people made that mistake. They chose the right equations or whatever, but used miles and hours for some stuff and meters and seconds for other stuff and feet for other stuff. So you need to get the units consistent. And it doesn't matter if you use miles and hours or meters and seconds or feet and seconds or whatever. It just has to be consistent. So I'm going to go to SI units because that's what I'm used to working with. So 20 miles per hour. We can convert from miles to meters. So I can go miles to feet. 1 mile is 5,280 feet. And then 1 meter is 3.281 feet. And then 1 hour is 3,600 seconds. And I think if you convert this, you get 8.94 meters per second. And we have to do 3 feet. If I'm going to do it in meters, we have to convert that to meters. 3.281 feet is 1 meter. So you get 0.914 meters. And now that we have everything in meters and seconds, we can set up our, so what are the things we have to choose in a one-dimensional kinematics problem? We have 4 choices to make. Yes, Well, we have to choose our position equals 0, which is different than the initial position. So just be careful with that distinction. P equals 0. I'm going to choose that on the ground like I always do. We have to choose our positive direction. And in free fall problems, I always choose up on that. And that's what I'm going to do. And then we have to choose our time equals 0 instant. That's when it's thrown or launched. So that's the instant it's thrown. And our time final instant. Okay, well, we're doing part A. And actually, this is a problem where our time final instant is going to change for part B. So for part A, we're asked how high the thing is at its highest point. So we have to choose time final to be the highest when it reaches the highest point. So that's the instant that it reaches a high point. And now we can think about what we know and what we want. So do we know time final? Do we know how long it takes to get to the highest point? No, but we don't care about that if we don't have to get it. We do know the acceleration. Since my positive direction is up, the acceleration is negative 9.81. The initial position is 3 feet, which converts to 0.914 meters. What we're trying to find is the final position. The initial velocity, well, we know the speed is 8.94. Now we have to think about the direction because we have to take that speed and turn it into a velocity. Is it moving in the positive or negative direction at time equals 0? Positive. Do we know velocity final? Yep. So that's how we specify that we're talking about the high point. So V final is equal to 0. And the equation that works with this stuff says 2a times the quantity PF minus PI is equal to VF squared minus VI squared. So we have 2 times negative 9.81 times the quantity PF minus 0.914 is equal to 0 squared minus 8.94 squared. And we get, if you solve this for PF, you get PF is equal to 4.99 meters. So 16 feet or so. And then you are asked for this height in miles and in scientific notation. So now we have to convert this back to miles. So 4.99 meters. 1 meter is 3.281 feet. And 5,280 feet is 1 mile. And so you get 3.1 about times 10 to the minus third miles. Any questions about part A? You know, really, if you did it right, I mean, you could do 3 times 10 to the minus third. I mean, I just want you to do the steps right. But if you, that's not as valuable to me. Um, and then for part B, it asks how much time it takes for it to go from being thrown up in the air to hitting the ground. So the key thing here is, um, we can still keep a lot of this stuff the same. Our p equals 0 can still be the ground. Our positive direction, I'm still going to use up. Uh, our time equals 0 instant, I'm still going to use when it's thrown. But I don't have any choice but to change my time final instant. We can't do part B if we keep the same time final. So time final this time is going to be when it hits the ground. And that means that you can't use any of, you can't use the height that you got in part A. You can't use any of your final information for part B. So what do we know and what do we want? This time we're looking for time final. We still know the acceleration is negative 9.81. We still know the initial position is 0.914. This time P final isn't what we got in part A. P final is the ground, which is 0, since I put my 0 at the ground. V initial is still 8.94. V final, we don't know anything about. So what can we do with this? We can use the equation that says P final is equal to P initial plus V initial time final plus 1/2 A times time final squared. So we have 0 is equal to positive 0.914 plus 8.94 T final minus 4.905 time final squared. And the easiest way to do this is really the only way I would say any of you should solve this is quadratic formula. So this is your A, this is your B, this is your C. And if you solve that, you get something negative. So negative like 9 seconds. Okay, so we know we don't want that one because we don't use negative times. And the other one is 1.92 or so seconds. And it asks for this in minutes. So this is the one that we want. 1.92 seconds, where 60 seconds is 1 minute, gives you about 3.2 times 10 to the minus second minutes. Any questions about that one? Then number 2 is just straight vector problems. You're given a vector that makes an angle of 40 degrees with this vertical. So this angle is 40 degrees, and the length of the vector is 10. And you're asked to calculate the components of this vector in two coordinate systems. The first one has the x-axis pointing to the left and the y-axis down. And the second one has the x-axis pointing down and the y-axis to the right. And in both cases, you draw the vector in its original orientation. So don't rotate the vector with its tail at the origin. So there's the vector for part A. There's the vector for part B. And in both of these, you're given the angle with the vertical. And now the angle that you want goes from the x-axis, whichever one you're using in that problem, and go to the vector. So that's the theta that you want for part A. That's 90 plus 40. So theta is equal to 130. For part B, you're just going straight from the x-axis to the vector. So your theta in this one is just positive 40. So for part A, you have the magnitude of the vector times cosine and sine of 140 degrees. And for part A, you get negative 6.43, 7.66. And for the second one, it's 10 times cosine and sine of 40 degrees. And that is 7.66, 6.43. Yes, sorry. Okay, and then number 3. So this is the one where it's rolling off a table. And we want to know the horizontal distance between where it rolls off the table and where it lands. So this distance is d, and we're trying to find that distance d. And we know that this height is 1 meter. And we know that it leaves the table with speed of 10 meters per second. Okay, so I'm going to choose a coordinate system. This one we have to do as a two-dimensional problem. I'm going to put my coordinate system on the ground right beneath where the ball is when it leaves the table. Okay, so there's my x-axis and my y-axis. Then time equals 0 is when it leaves the table. Time final is when it hits the ground. And the coordinate system, the origin and the coordinate system orientation are both shown. And one key thing that you need to recognize to do this problem is that it's going, since it's rolling horizontally along the table, at the instant it leaves the table, it's going to have a totally horizontal velocity. And so that velocity vector is going to be, 10 times cosine and sine at 0 degrees, or you can just think of it as in the positive x direction. So it's going to be 10, 0 for a velocity vector. We don't know time final, and we're okay with that. The acceleration vector in the coordinate system I chose is 0, negative 9.81. The initial position vector is 0, 1. The final position vector, we're trying to find pfx, and we know that pfy is equal to 0. The initial velocity vector is positive 10 for x and 0 for y, and we don't know the final velocity vector. Okay, there's no equation that works for finding pfx, so we have to try to find tf and see if we can use that to give us an equation that works. What? Yeah. No, because as soon as it touches anything, we can't use the free fall equations anymore. So we're always basically calculating stuff until the instant before it makes that first contact. Okay, so we want to find TF. And we can do that with the equation that says PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 1 plus 0 minus 4.905 TF squared. And if you solve for TF, you get plus or minus 0.451 or 2. I think it's 2. We always use positive times, so we're going to choose the positive one. And now that we know TF, we can include that in our list of variables that we know. And now we do have an equation that works for finding what we want, PFX. So PFX is equal to PIX plus VIX TF plus 1/2 AX, blah, blah, blah. AX is equal to 0. So we don't care about that. That's going to go away. And so we have that PFX is equal to 0 plus VIX is 10. TF is 0.452. So PFX is 4.52 meters. Any questions about that one? Oh, great. I remember grading that. Yeah. So bring that up after and I'll fix it. The initial position, so it's a two-dimensional problem. And so it's an initial position vector. The x component is 0. The y component is 1. Okay, and then the last one is 4. And that's the one with the pretty crazy hard extra credit problem. So the idea is this object is launched from a height of 4 meters. at an angle 10 degrees below the horizontal. How long does it take to hit the ground? So here's the ground. The object is launched from a height of 4 meters. And if this is the horizontal, the object is initially launched at an angle 10 degrees below the horizontal. So that's the angle it's launched from. And from there, the path it's going to follow is going to be a concave down parabola, something like that. Also, given for part A, for the main part of this problem, the speed at launch is 10 meters per second. Okay, so that initial velocity vector is 10 meters per second. And we want to know that elapsed time. Okay, so the coordinate system is going to be, I'm going to put it on the ground right underneath where it's launched from. Okay, so we're trying to find time final. The acceleration vector is 0, negative 9.81. The initial position is 0 for x, 4 for y. The final position, we don't know the x coordinate, but we know p, f, y is 0 because it hits the ground. The initial velocity we're going to have to calculate from cosine and sine. So to calculate that one, we're going to have the speed times the cosine and sine of some angle. Okay, so let's look at, so I drew the initial velocity vector here. The coordinate system, if you put the tail of this initial velocity vector at the origin, it's going to look something like this, you know? And so what's the angle to go from the positive x-axis, which in this case would be that dotted blue line, from the positive x-axis to that initial velocity vector? 350 or negative 10, either one of those. So cosine and sine of 350. And that gives you 9.85, negative 1.74. So that's the initial velocity vector. 9.85 is the x coordinate. Negative 1.74 is the y. And then velocity final, we don't know. So we're looking for an equation that works to solve for TF. And the one that looks like it works is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So you get 0 is equal to 4 minus 1.74 TF minus 4.905 TF squared. A is negative 4.905, B is negative 1.74, C is positive 4. And if you calculate that using the quadratic formula, you get negative something and positive 0.743. We know we're not going to use the negative one, so it has to be this one. Any questions about that one? So that's the main part of that problem, and then there's an extra credit part that was kind of absurdly hard. Nobody got it all the way through, although a couple of people sort of started out on the right track, but not very many. Yeah, right. She was one of the few that sort of started in the right direction. So let me go through the extra credit problem, but this one isn't something you need to worry about, but let me explain how to do that. So the extra credit part said, how fast would it have to be launched in order to hit the ground 5 meters away horizontally? So how fast so that it's 5 meters away horizontally when it hits the ground? Okay, so I'm going to use the same setup. My time equals 0, my time final, my origin location, and my coordinate system orientation. These are all going to be the same. Okay, so now we're going to have to figure out with the new stuff that's given, what do we still know what's new? So time final, we still don't know. And in this case, if we can get away without time final, that's fine with us. The acceleration, we can always count on that acceleration vector, no matter how hard the problem is. The initial position is still the same. So PI is equal to 0, 4. P final, we actually know more than we did in part A. So far things are looking really great. P final, we know that the X position is going to be 5. It's going to land 5 meters away horizontally. And we know that the Y coordinate is going to be 0. So far this problem's looking easier than the first one, but that ends abruptly right now. The initial velocity, okay, well, we're going to have to calculate that. So what do we know about the initial velocity? Well, our coordinate system is oriented like this. And our initial velocity vector, it still makes a 10-degree angle with the x-axis. It's 10 degrees below the horizontal. We don't know what the magnitude of that is. In the first part, we knew that the magnitude was 10. This time, we don't know what it is. I'm going to call it capital V. That's the speed. Okay. So what do we know about this velocity vector if it has a magnitude of V, and we know that the angle, the counterclockwise angle from the x-axis to the vector is 350. That's right. So V times cosine of 350, V times sine of 350. And so that gives you 0.985 V and negative 0.174 V. And where do you put that? This sort of messes with the way we normally, I fill out what we know and what we want. What we've done here is we've basically taken a velocity vector where at first we didn't know either component. And we've said, well, we don't really know either component, but we can make it, we can express it in a way that there's only one unknown thing. So I'm going to put this here and stuff that we know because we know something about it, but okay. And then what are we trying to find? We're trying to find this V. Okay, I don't know. That's about as good a way I can think of to separate this up into what we know and what we want. If we knew this V, we would know VI, but we have to solve for that V. Okay, well, is there a way to, so basically, is there an equation where we can have one of these expressions in terms of V in it and everything else is known? And there isn't anything. So our next, so no equation works. So you can give up. But how about finding time finals? And in that case, you can set up two of these equations. Well, Pfx is equal to Pix plus Vix Tf plus ... And you can also set up Pfy is equal to Piy plus Viy Tf plus 1/2 Ay Tf squared. And what I'm going to do is I'm going to come up with an expression for Tf from this first one, and then I'm going to substitute it into the second one. And we're going to set this up as a system of two equations for two variables. And the two variables are going to be time final and V. I'll call this one equation star and double star here. Okay, so equation star. We know that Pfx is 5. Pix is 0. Vix is 0.985 times the speed. And then we're multiplying that by Tf. And all the other stuff goes away because the x component of acceleration is 0. And so we can rewrite this equation as an expression for Tf, where Tf is equal to 5 over 0.985 v. And now I'm going to substitute that into equation 2 star, which says 0 is equal to 4 plus, okay, so VIY is negative 0.174 V. And TF, I'm going to substitute this expression in. So 5 over 0.985 V. You can see in this case, these V's cancel, so that's good. And then plus 1/2 times AY is negative 4.905 times TF squared, which is this squared. So 5 over 0.985 V all squared. So 0 is equal to 4 minus, can someone multiply out these numbers? So 0.174 times 5 divided by 0.985. Okay, 0.883. And then this, so you have to square all this stuff and then multiply by 4.905. So let me write it out in one more step. So 4.905 times 25 over 0.985 squared over V squared. What a mess. (126.4) over V squared. And now we just have to solve that. It's in the right ballpark anyways. About 125 divided by 1. So, okay, so 126.4 is equal to 3.117 V squared. So V squared is equal to 126.4 divided by 3.117. And so you take the square root of that, you get plus or minus, hopefully 6 point something, because I think I remember that. I'm going to call it 6.3. I don't know, because that's what I remember, somewhere in there. This is a speed, so we want the positive. So in order to make it land 5 meters away, it needs to have a speed of 6.3 meters per second. Okay. What? Oh, okay. Oh, yeah, yeah, yeah. Right. It's like, yeah, 40 and then square root of 40 is 6 point something. Okay, so that's how you do a problem like that, but that's a pretty hard problem. Uh, really, it was a mistake that ended up on the test. I made a little modification to a problem, and I didn't have time to go through the test for the night class. And then when I did it in class while the test was going on, I was like, oh, hell no. And so then I quickly changed it to extra credit on the fly during their test, and then I gave it to you as extra credit because they had the chance or whatever. But that I don't want you to feel like that's a problem. I expect you to be able to think your way through. But it uses the same ideas. It's really the mathematical thinking that's tricky about it more than anything. Anybody have any questions about that? Okay, well, let's just stop there. And then Thursday, I'll go through Newton's third law, which we've already seen in a lot of forms before, but I'll talk about it sort of for the first time. And then exam 4 is on Tuesday. So, and it will involve all the stuff up through um, Newton's laws, I think, are what the problems are called. Maybe Newton's second law, but all of the problems involving uh, pushing and pulling forces and friction. Any questions? Okay, that's it.